Welcome to Lecture 4.4, Curve Sketching for Calculus 1. What we're going to do in this section is learn how to use all the information we've already learned previously in Chapter 4 about derivatives and what they tell us about graphing, use some of our prior knowledge from algebra, and then we're going to try to graph a function with this information. Now what I'm going to go through are a bunch of steps that are really guidelines, and if you go through all the steps, if you can do them, it should cover everything you need to graph a function. But not all will work on every function, and so we'll try them and we'll see some of this working out. We'll do an example together. So the first thing you probably want to do is find a domain. You want to find all values of x that are valid for whatever function. Now remember, when you're trying to find the domain, we typically look for two things. We look at two types of equations. Is it a rational expression where a denominator cannot equal 0? Or is it an even-rooted radical, a square root or a fourth root, for example, where the radicand, what's inside the house, so to speak, has to be greater than or equal to 0. It has to be positive because you can't take the square root of a negative number. So in this example here, where f of x equals the square root of x plus 2, we set the radicand, what's inside, greater than or equal to 2, and solve. So the domain of this function here is that x must be greater than or equal to negative 2. So this is what we're going to be graphing along the x-axis. The next thing we're going to do is find the intercepts. We're going to try to find where the function crosses the x and y axis, the x-intercept and the y-intercept. Remember, to find the y-intercept, we simply plug in x equals 0 into the equation. This is usually the easiest one to find. And in this case, we get the square root of 0 plus 2 is the square root of 2. So our y-intercept here, where's my arrow? Our y-intercept here is 0 square root of 2. Okay. For the x-intercept, remember we set y equal to 0, which is setting the entire equation equal to 0 and solving. So if we square both sides, we get x plus 2 equals 0 squared, or 0, and so x equals negative 2. So the x-intercept for this equation is negative 2, 0. Okay? So we want to go ahead and graph these 2 points. As we're going through this step, we want to start building our graph. We don't want to do all the work and then come back. It could get a little confusing. And if we start graphing points on the graph, points and data, this will also help us start to see the function kind of come to life in steps. Okay. The next step is just to test for symmetry. This could help us with graphing the function. And this means, is it reflected across the origin? Is it reflected across y? Or is it periodic? Remember that functions cannot be reflected across x, because that by definition would make them not a function. So when there is y symmetry, we call this an even function. And that what happens is, when we substitute in a negative x into the equation, we get back to the same equation. So notice that f of negative x is the same as f of x. So when we look at this equation to the right, x squared plus 4, if we substitute negative x in for x, we get the quantity of negative x squared. Well, negative x times negative x is just x squared, so we get back to the exact same thing. So this is an example of y symmetry. Origin symmetry, which we call an odd function, and an easy way to remember these for me is that origin is odd and they both begin with the same letter, so y symmetry is the opposite one, even. And here, when we substitute in negative x into the original function, we get the negative, or the opposite of the original function. Okay, we don't get back to the original function like we do with y symmetry. We get the opposite value of the function. So here we have negative x, we have x cubed as our function. Notice if we substitute in negative x for x cubed, the x, we can pull out the parts and do negative 1 cubed times x cubed. Well, negative 1 cubed is negative 1. And so when we plug in negative x, we actually get negative, or the opposite of x cubed. So this is an example of origin symmetry, or an odd function. Periodic function is one that just repeats over the period. A good example of this would be the sine function. Next, we're going to try to find asymptotes. Now remember, horizontal asymptotes, these are horizontal lines, these are y constant values, are what happens to the function when it goes to infinity or negative infinity. We started this class looking at how to solve these kind of limits, so you should know how to solve this algebraically. For example, if the function is 2x over x plus 3, to solve this algebraically, we would divide both the numerator and denominator by the largest power of x in the denominator. And so we get 2 over 1 plus 3 over infinity, or 3 over x, excuse me, and then as x goes to infinity, that second piece of the bottom term goes away, and so we just get y equals 2. So this is a constant line, y equals 2. We want to go ahead and graph asymptotes. Remember from algebra, we graph asymptotes with dotted lines. So we're going to have a horizontal line at y equals 2. For vertical asymptotes, here what we do is, these are typically with rational equations, or excuse me, rational functions, which are fractions. We set the denominator equal to 0 because this is not allowed, and we solve this. So x plus 3 equals 0 gives us x equals negative 3. So at negative 3 we have a vertical asymptote. Next we're going to take the first derivative. Remember that the first derivative tells us about local maxes and minimums. So if we take the first derivative of this function, we get the derivative f of x, or f prime x, equals 2x. Okay, then we set that equal to 0. 2x equals 0 when x equals 0. So we know we either have a local max or a local min at 0, 2. We can also find the intervals of increase or decrease. When does f prime x, when is the derivative of f of x greater than 0? And a good idea here is simply to plug, you can do this algebraically, which is what I've done, or you can plug this into your calculator and look before and after the x value and see what's happening. So here we see that the function is increasing. It's positive when x is greater than 0. And so this should actually say 0 to infinity, not 2 to infinity. So this is actually wrong here. So this function increases from 0 to infinity because its x is greater than 0. The intervals of decrease, we do the same thing. Here we figure out where the derivative is less than 0. And so you can actually solve it algebraically, putting the derivative, which is 2x, making it less than 0 and solving it algebraically. Or you can plug the derivative, 2x, into your calculator and figure out where it's going from positive to negative. Also, this interval of decrease is also wrong. It should be negative infinity to 0. These both should be 0 here. Okay. Then we look at the second derivative. Remember, the second derivative tells us about concavity and also about points of inflection. So the first thing we're going to do is take the second derivative. The first derivative is 3x squared. The second derivative is 6x. Okay? Now we can try to figure out where this is concave up and concave down. Remember, where the second derivative is positive, we have a concave up shape, or the spoon facing up. Where the second derivative is negative, we have a concave down shape. Again, we can solve this algebraically if it's simple. And also, we're not going to do this unless it's really easy to calculate. Okay? If we have some really horrible functions where the derivatives are not easy to calculate, we're just not going to do that part of this. Also, we want to find the points of inflection if possible, and that's by setting the second derivative equal to 0. This is what we learned in the last section. And in this case, we get x equals 0. And when x equals 0, what does the original function equal? It equals 2. Okay? The last thing we're going to do is sketch the graph. Okay? So let's go through an example here and actually do a whole problem with the same function and see what's going on. First thing we want to do is find the domain. Remember, we find the domain by finding values of x that aren't allowed by setting the denominator equal to 0. We get x squared equals negative 1, or excuse me, x squared equals 1 when we solve this equation. X squared cannot equal 1, so x equals the square root of 1, which is positive or negative 1. So x cannot equal positive or negative 1. So this means that this function can go through all values except positive or negative 1. This is also a hint later for asymptotes, but we'll see that in a minute. Find the intercepts. Remember, we find the y-intercept by setting x equal to 0. When we put 0 into this equation up here, our original function, we get 0 over 0 minus 1. 0 over negative 1 is simply 0. So our y-intercept is 0, 0. Okay? For a rational function to find the x-intercept, we set the numerator equal to 0 because we want to know what's happening when y goes to 0. And so 2x squared equals 0 gives us x equals 0. So we have this actually same point. So both the x and the y-intercept are the same. And of course we can see that because it goes through the origin, which is the only point on the graph where both the x and y axis intercept. Okay. So we look for symmetry. When we plug in negative x, what happens? Do we get back to the same function, or do we get to the opposite of that function, or neither, where we have no symmetry? So notice when we plug in negative x squared just gives us x squared, negative x squared gives us x squared, and notice we're back to the original function. So this is even symmetry. This is telling us that this is going to be reflected around the y-axis. The y-axis is going to act like a mirror, and we should see the same side on the left and on the right. For vertical asymptotes, we're going to look at, we set the denominator not equal to 0 and solve. Notice this is how we also found the domain. And we have two values, plus and minus 1. So these are our first, we should have graphed the intercept. We should now graph the asymptotes with dotted lines. The horizontal asymptote is as figuring it out the function as x goes to infinity. Again, remember with evaluating limits at infinity, we solve these algebraically by dividing the numerator and denominator by the largest power of x. So we get 2 over 1 minus 1 over x squared in the denominator. Well, 1 over x squared goes to 0. Remember, as x gets really, really big, and that's in the denominator, 1 out of infinity is 0. Just like your chances in the lottery, right? 1 out of a billion or whatever. So now that we have this data, I'm sorry, we still have to find our derivatives. We're only on step 5. I skipped a little bit ahead. Now, rational functions are sometimes a little bit more difficult to solve algebraically or to find the derivative. Remember, this is the quotient rule. You can see all the pieces there, and when we simplify it, we get negative 4x divided by the quantity of x squared minus 1 squared. Now remember, we find the derivatives so we can find the local maxes and minimums. We find the local maxes and minimums by setting this equal to 0 and solving. Okay? Remember that what we're looking for in critical values are where does the function not exist, or where does the function equal 0. To find where the function equals 0, we set the numerator equal to 0 and solve, and we get the first critical value of 0. To find other critical values where x doesn't exist, we set the denominator equal to 0 and solve. And when we do that, we get plus or minus 1, which we saw in an earlier step. Now what we want to know is what's happening before and after, right? Because these are our local maxes and minimums. This is telling us where they occur. And now we want to figure out at each point, is it a maximum where it goes from positive to negative slope or first derivative, or is it a minimum where it goes from a negative to positive slope or first derivative? Again, we can plug in these values. We can pick a value in each of these intervals because these are our critical values, or we can simply plug in this function into our calculator, set the table up so it's going by half units instead of full units, and then see what's happening in each piece. In the first, before negative 1, the derivative is increasing. Between negative 1 and 0, it's also increasing. So we don't have a we don't have a local max or minimum here, right? We have a horizontal point of inflection. Between 0 and 1, we have a function decreasing. So at 0, notice we have increasing for before and decreasing after, which means that we have a mountaintop increasing, then decreasing. We have a mountaintop or a maximum at 0. And then when we look at the last section, x is greater than 1, we see that the derivative is less than 0, which means it's also decreasing. So again, here at 1, it's going from decreasing, so we do not have a max or minimum. We have another horizontal point of inflection. And then we take the second derivative. Again, remember we want to find the critical values here too, so we can figure out where it's moving from concave up to concave down. Once we've done that, and we solve this the same way, we look for the values in the numerator and denominator. Then we can plug this into our calculator and figure out what's happening before -1, between -1 and 1, and then also greater than 1. And so we can see the graph goes from positive to negative to positive. So between positive and negative, remember we have a mountaintop. So this at -1 we have a local max. But then in the second piece, from negative values for the second derivative, and then positive values, we go negative then positive. This is a valley. So at 1 we have a minimum. We also know this is concave up when they're positive, concave down, and then concave up. And so here's the graph that we see there as we're building this. Remember that between -1 and 1, we saw that it was symmetrical around y. Here you can see the asymptotes y equals 2, x equals -1, and x equals 1. So once we get to this last point here and we've done all of the work, we might actually take I lost my train of thought. I'm not sure what I was going to share with you there. So here we've got the graph. We can see that it's concave up, concave down, and then concave up, so it's matching our data. Once you've got all these pieces done, you might want to go back and find a value or two along the way. Sometimes this is very valuable. Like, for example, in this graph, there are actually no points even plotted except maybe the origin. And so this matches with all that we learned about this being a max, etc., and the asymptotes and all. So these are just pretty labor-intensive, step-intensive. So if you need to, go back and review the video again. So remember that what you're going to do is find the domain, then find the x and y intercepts, see if there's any symmetry to help you graph, find the asymptotes, horizontal and vertical, find the first derivative, which gives you the locations of max and minimums if there are any. It also tells you where it increases or decreases based upon the sign before and after the critical values. Then we take the second derivative to find if we're going concave up or concave down and finding inflection points, and then we can sketch. Now really we should be sketching all along here. We don't want to get to the end and have to go back and figure out what we did.